So this is a video on back titrations. We're going to look first of all at the rationale. So why, in other words, do we use back titrations? You've studied other types of titrations, acid-base, for example, and redox, and we're going to have a look at why we would choose a back titration, and then we're going to look at the worked example. So I'm going to work my way through a few questions on back titrations. I'm going to show you the answers as well. You probably might want to pause the video at the questions and then do them yourselves and then check the answers. And I'm going to finish off with an extension question on the back titration, a fairly difficult one. And I would imagine this, so if you're happy that you can do all of those questions and understand why we use back titrations, then you have met what you will be asked. Okay, so let's have a look, first of all, why we actually use a back titration. So if you remember back to AS level chemistry, you did titrations where you did acid-base. And what you did with your acid-base titrations very simply was you took your conical flask and you had your solution of your unknown substance in that, whether it be an acid or an alkali, and you also had then in your burette, you had either your acid or your alkali, and that was also in solution form. So in other words, everything that you were either titrating with or analysing was in solution. So therefore they were soluble in water. Now there's lots of things that are not soluble in water, but you still want to analyse them in terms of their percentage purity, okay, or the percentage biomass or similar. So therefore we cannot use a titration in the traditional sense that you would have used last year. So we have to adopt a different strategy. And that different strategy is the back titration. So let's have a look at the left-hand side. We have a known mass of an insoluble sample. So this thing, in other words, insoluble in water, it doesn't dissolve in water. Okay, so we can't analyze it in the normal titration method. So what we'll do is we will take that and we will dissolve it into something that it does dissolve in. So it's got to be able to dissolve in either acid or alkali. And in this instance, I've chosen to dissolve it in excess acid. Now, we have to dissolve it in a known volume of acid and a known concentration of acid, because in this instance, we've got to know the number of moles of acid that we're going to dissolve this thing. Okay? So remember, number of moles is equal to concentration times volume over 1,000. So I've got to know the concentration and I've got to know the volume. Okay, and the other thing I need to know about my original sample here, as I should have said, was I got to know the exact mass of that sample. Okay, so after that then what we'll do is we will pipette a certain amount out of this solution. Because what we've done now, let's take an example, and let's say my solid here was zinc solid to begin with. Okay, so we're starting off with zinc solid. Now we'll have to say it's an impure sample of zinc, and we're trying to find out exactly how much of that impure sample is just pure zinc. So when I take that and I react that with acid, what I've now done is I have dissolved all of that zinc to give me aqueous zinc chloride, plus I'm going to get some hydrogen gas. Now, my zinc metal is now all dissolved, it is all reacted. And because of what I said here, I know the number of moles of hydrochloric acid that have been used to dissolve it. The next thing I will do is out of that reaction mixture that was used here, I will pipette. Usually the volume that we would use is 25 cubic centimeters. That's not to say that that's the volume that has to be used, but 99 times out of 100 in an exam question, that's what we use. And that 25 cubic centimeters will go into our conical flask, and we will now carry out a normal acid-base titration. So in this particular one, remember we said back here that the acid that was added to the zinc in this case was in excess. So therefore we are going to have some unreacted acid in my conical flask. We're going to titrate that against a standard alkali, okay? And of course we're going to be able to know what volume of standard alkali was needed to neutralize the unreacted acid, because we're going to measure that as our burette reading, and we're going to probably carry out an accurate, or a couple of accurates, and get ourselves a couple of concordant titrations, hopefully, and therefore get an average. Okay, so Once I get my titration value here, I know, so if let's take it, use sodium hydroxide, okay, and to titrate against my unreacted acid, and that will give me, okay. Now, if I was to write the full ionic equation, because I said we would use hydrochloric acid here, it's going to be as so. But the key thing in both instances is they react in a 1-to-1 ratio. So whatever number of moles, which can be calculated by the volume, multiplied by the concentration of my sodium hydroxide over 1,000, that will give me the moles of sodium hydroxide, which will also give me the moles of hydrochloric acid. Now that tells me how many moles of hydrochloric acid were left over at the end of this reaction here, or in other words, how many were in excess from the zinc, okay, from the reaction with the zinc. Now, I know how many moles of hydrochloric acid I started off with, because if you remember here, we said we would in step 2 here, we knew the volume and the concentration of hydrochloric acid that we were going to begin with, okay, and because of that, I know the moles of hydrochloric acid I started with. I now know how many moles of hydrochloric acid I have left over at the end. In other words, left over that did not react. So if I know moles that I had to begin with, if I know moles that were left over at the end, I can take those two things away from each other, and that will give me how many moles of hydrochloric acid did actually react. Once I get the moles of hydrochloric acid that did react, I can use the ratio, as you've always done in your moles calculations, to work out how many moles of zinc were in the original impure piece of zinc. Once I get the moles of impure piece of zinc, I can simply do mass equals moles times RFM. That will give me the grams of zinc, okay? And from there on in, I can simply do the mass of the pure zinc divided by the entire mass of the sample, and that will give me the percentage. Anyway, we're going to do some examples here. We're going to take zinc as an example. Okay, and what we've got here is a company that's going to sell some zinc to us. They're telling me that it's 92% pure zinc, and you as a chemist have been tasked to investigate to ensure the quality control and that zinc is in actual fact 92% pure. You're going to get yourself a 6-gram sample of that impure zinc. And the first thing you will do, as we said on the previous slide, is you will react it with an excess of acid. And we're going to use hydrochloric acid here. And the first thing we got to do is get the balance symbol equation. We had it on the previous slide. There it is again. And what we're saying here is we're going to work with 100 cubic centimeters of that. Okay? And we're going to use 2.0 moles per decimeter cubed acid. So in other words, what that means is at the start, okay, I am going to have initially, okay, we're going to have 0.2 moles of acid reacting with my zinc. My zinc sample, my impure zinc sample, 6 grams. I've got to find out how many grams of actual zinc are in that 6 grams. So let's get going. Okay, the chemist then took that amount of hydrochloric acid. So we reacted my hydrochloric acid with my zinc. Okay, so some of the hydrochloric acid reacted as per this equation here, but because it's in excess, there will be some left over. Okay, and we reacted the leftover hydrochloric acid with a 25 cc sample of it, okay, with 0.5 mole per decimeter cubed sodium hydroxide, and the average titer was 19.8 cubic centimeters. So therefore, N equals CV equals volume times concentration. That's how many moles of sodium hydroxide we use in the titer. It's a 1-to-1 ratio of sodium hydroxide to hydrochloric acid. So that's how many moles of hydrochloric acid were in my 25 cubic centimeters from up here. But remember, we go back to the original question, it was in 100 cubic centimeters. So if I go to the next part, I need to work out how many moles of hydrochloric acid were left over and unreacted in my 100 cubic centimeters. So I take my moles in 25 and I multiply them by 4. And that tells me I have 0.0396 moles in 100 cubic centimeters of that solution unreacted. So I know moles to start with, 0.200. Okay, I know moles that were left over at the end, 0.0396. Okay, I know therefore the moles of hydrochloric acid that did actually react, because it's that minus that is 0.1604. Okay, I then can work out using my balance symbol equation from the previous slide the moles of zinc, because it's 2 moles back to 1. So the moles of zinc in my original sample were 0.1604 divided by 2, so 0.0802 moles of zinc in my original 6 grams of zinc. Simply convert my moles of zinc into mass of zinc by multiplying by the atomic mass. Gives me that. The original sample was 6 grams. Okay, I knew I had 5.213 grams in my 6 grams. The percentage, therefore, is 36.9% of that zinc is actually pure zinc. So the people say they're selling us 92% zinc. They're not. They're making a few extra pounds where they shouldn't be. So that's an example. Right, I'm going to run through 4 examples now, 4 questions now. If you think you're happy enough to do them, okay, I suggest that you pause the video and you just get on with them. Okay, what I will do is we'll start off with a couple to begin with, which are very structured, so split up into steps, and then we'll move into a couple at the end which are very unstructured. Okay, and those will be more sort of similar to what you would get in an A-level chemistry question, the unstructured ones. So there's a question. You might want to pause the video and have a go at that now. Okay, so I'm going to move on to the answer. Okay, so that's the answer there. If you had to write the balance symbol equation first of all, okay, to get yourself going. The moles of, what was it in this instance? The moles of the sodium hydroxide, okay, that were added, okay, to the 25 cc sample were just concentration times volume. So that was the moles you started off with, okay. If we look at that, then what we did was you titrated that against the excess moles of sodium hydroxide against acid, 20 cc's of 0.2 acid. So the moles of hydrochloric acid were that, okay, which meant there was that amount of unreacted sodium hydroxide because they're in a 1-to-1 ratio. The number of moles of sodium hydroxide, that I started off with that. The moles of sodium hydroxide I had left over unreacted or in excess is that. So there you go, there's your moles of sodium hydroxide that reacted in a 1-to-1 ratio with the ammonium chloride, remember? So the moles of ammonium chloride are the same, 0.02. The concentration of the ammonium chloride then is your moles divided by the volume. It was 25 cubic centimeters, if you remember, was the solution of ammonium chloride that we began with. So there's my concentration in moles per decimeter cubed. Remember the question asked in grams per decimeter cubed. So you simply multiply the moles per decimeter cubed by the RFM of ammonium chloride. You should come up with the answer 44.9. Okay, have a go at this one. Okay, so again, very structured. Okay, very similar question, but yeah, very structured. There's a little step in this one that perhaps didn't exist in the last one, so just be careful of that. So I'm going to move on to the answer now if you want to pause this and have a go at it. So the first thing you had to do here was get the correct balance symbol equation. If you don't get those, you will not be getting this answer right. So the only trick in it was the magnesium oxide to hydrochloric acid was a 2-to-1 ratio. Okay, so the moles of hydrochloric acid you started off with concentration times volume was as so. So you started off with 100 cc's. You then reacted the unreacted hydrochloric acid, the excess hydrochloric acid with sodium hydroxide, and that required 19.7 cubic centimeters of 0.2 sodium hydroxide. So that was the moles of sodium hydroxide because it's a 1-to-1 ratio. Then that is also the moles of hydrochloric acid that are left over unreacted from this reaction up here. I now know moles of hydrochloric acid I started with. I now know moles of hydrochloric acid that were left over that did not react. So I can work out in part D the moles of hydrochloric acid that did actually react. That allows me then to get moles of magnesium oxide, okay, that were in the reaction vessel. So it's the moles of hydrochloric acid divided by 2, okay, which gives me this value here. And then very simply I'm looking to work out percentage purity. So I convert my moles of magnesium oxide, by multiplying the moles of magnesium oxide by the RFM of magnesium oxide, and then the percentage purity of magnesium oxide is the mass of pure magnesium oxide in the entire mass of the sample, gives me 96.6% purity. Okay, I think you can have a look at this one now. Okay, this one I'm not going to talk you through the answer to this one. I'll put it up on the board. You should be able to hopefully see the pattern and the rhythm of these questions now. So pause the video, have a go at that one. Okay. So there's the answer. If you got 60%, well done. The only thing in this one that perhaps was a little bit different than the last ones was that you had, if we go back to here, we used a 25 cc sample of the solution, okay, in the titration, but the original solution actually came from 250 cubic centimeters. So whatever moles were in this titration, we had to multiply that up by a factor of 10 to work out how many moles of unreacted nitric acid were in that particular titration, which worked out to be that number of moles of unreacted nitric acid. Okay, so the moles of nitric acid we started with were that, the moles that were left over unreacted were that. So there's the moles that reacted, divided that by 2, because remember back here we're going back 2 to 1 ratio. That gave me my moles of lead carbonate. We multiplied that by the RFM of lead carbonate to give us mass of lead carbonate. So it was 0.6 grams, and 1.0 grams gave me 60% purity lead carbonate. Right, the last question coming up here, as you can see, is completely unstructured, so something similar to like you would get in an A-level exam. So again, I would suggest you pause the video, read through it, okay, and have a go at it. I'm going to move on to the answer now. So the answer was 98.5% pure zinc, okay? So the only thing that was maybe a little bit different here, we did one similar with zinc earlier, was we had a 2 to 1 ratio there, okay? So my sulfuric acid moles were as so. My moles of unreacted sulfuric acid then were the moles, or the titration value here, okay, sorry, the titration value of the sodium hydroxide, okay, which is 18 at 0.2 molar, okay, so that divided by 2 to give me back to the moles of the sulfuric acid because of the ratio, okay, and that meant therefore that I had to then take this value and multiply it by 10, because again, if you see up here, we had that all in 250 cubic centimeters, but only 25 cubic centimeters of that unreacted sulfuric acid was actually used in the titer, so only 1/10 of the moles would have made its way into the titer. So we had to scale up the moles by a factor of 10 to tell us we had 1.8 times 10 to the minus 2 in 250. The number of moles of sulfuric acid I had to begin with was as so. The moles of sulfuric acid I had left over were as so. So I took those away, gave me moles of reacted sulfuric acid. That is in a 1-to-1 ratio with the zinc. Okay, you look at the top equation here, zinc to sulfuric acid, 1-to-1. Okay, multiply the moles of zinc by the atomic mass of zinc, gives me the mass of zinc in the sample, and then I simply work out the percentage. Okay, right, I'm going to put on here now an extension question. I'm going to put it up here, and that is just the question, completely unstructured. If you're looking at that and you really completely have no idea, I'm going to go through the structuring of the question on the next slide. So if you want a real challenge, just pause the video now and have a go at it. If you don't think that you can get the answer from the information that's on the board, you need a little extra help, the structured part of the question is going to come up, okay? And then I'll move on to the answer. Okay, so pause the video now if you want to have a go at it in its most difficult form. So the structured parts are as so you might want to pause the video now. I will go through the structured parts. So perhaps pause that video now and have a go at those parts. And then those are the next two parts. Pause the video now, I'm going to move on. And that brings you right through to the final parts. So those are the parts that you've got to work through in order to get to the answer. So I'll go through the answer now. Okay, I'm not going to talk you through it. It's all, I think, fairly self-explanatory. Okay, that D is divided by 3. I think it's maybe missing off the screen there. Okay. And that is the next part. Okay. So pause it if you need to, and then I'm going to move on. And there you go. That's the final answer. So if you got 22.8%, really well done. That's a really tricky question. Even for A level, a lot of people really struggle with that. They certainly, if you got it right without looking at the structured parts of the question, you've done amazingly well there. If you got it right, even by working through the structured parts, you've done pretty well as well. Okay. And if you didn't get it right, hopefully you can see where you went wrong. Okay, so that's the end of the PowerPoint of back titrations, guys. I hope you found that useful. Okay, there's lots of ones to practice in your past paper questions, etc. So please do that.